In the previous lessons, we learned that the fundamental components can be used to produce any objects within the vector space. In other words, we can say that these fundamental components span the vector space. In layman term, you can get any objects in the vector space just by combining the fundamental components with different ratio or formulations. Let's use our red concrete case for our study here. In the previous video, I showed you that you can get any members of red concrete cement at 10%, 20% or 30% just by mixing the four fundamental components: water, sand, gravel, and cement at different formulations. So geometrically, let's imagine that W is a vector space or a family of objects or vectors, and the fundamental component is V. So by using the V component here, you can multiply it with any scalar to obtain a new members that is along this W line. And when you connect all the new members together, you actually will get back the W vector space, the line here. And for the polynomial equations, let's consider the case of P4. I can say that the polynomial of fourth order is spanned by 5 components here. One represented by the x0, x raised to the power of 0, and x squared, x cubed, and x fourth. So by using these 5 components, I can get any polynomial equations. P1 equals to 1 plus x, P2 equals to negative x plus x raised to the power of 4, and P3 and P4, as long as the highest power is raised to the power of 4. So for P2 here is actually a combination of negative 1 multiplied with x plus 1 multiplied with x 4. Or for P3 here is 1 over 2 multiplied with 1 plus 1 multiplied with x cubed. Or the P4 here is negative 3 multiplied with x squared plus 1 multiplied with x fourth. The missing part of the components here, the x squared, x cubed, and x raised to the power of 4 for P1 is actually 0 multiplied with x squared, 0 multiplied with x cubed, plus 0 multiplied with x raised to the power of 4. So you can get any polynomial equation just based on these 5 fundamental components, just like the case of your red concrete here and the case for this W vector space here. So how are we going to test for the spanning, whether the given set of vectors that span the system or not? So for example, to determine whether the V1, V2, and V3, the given vector here, span the vector space of three-dimensional space or not. So we must determine whether an arbitrary vector in R3 can be expressed as a linear combination. The reason that we are using A as an arbitrary vector is because we don't know what kind of objects that we should refer to, because the combinations of V1, V2, V3, if they truly span the system, you can get infinitely many solution or many output of the A here. So to be safe, we let it be an arbitrary vectors of A1, A2, and A3 that could be produced by combining the V1, V2, V3 at different ratio. So I'm going to write it into this form, and similar with the previous exercise, you have to match it component by component. A1 with the first entry here, A2 with the second, and A3 with the third one, and you end up with a system of linear equations here. You have to solve this system of linear equations, and depends on the solution you have. So your decision whether the given three vectors V1, V2, V3 span the system or not will be met. Now take a step back and ponder over. If you have this system of linear equations, if the vector V1, V2, V3 span the vector space, you should be able to use it to produce any vectors in that particular vector space. So if vector V1, V2, V3 truly span the vector space, we should be able to obtain a vector A, which is a linear combination of V1, V2, V3, which means that A is expressible in terms of V1, V2, and V3. Hence, what kind of solution should we have for the system of linear equations? Well, if the system is consistent, you'll be able to solve the system of linear equations here. If it is inconsistent, what does it mean? Try to pause the video and recall back from the lesson that you learned from the equivalence statements. think about it. In this case, we can use the determinant to solve the problem here. If the determinant of the coefficient matrix A here equals 0, it means that the system of linear equation is inconsistent, and so v1, v2, v3 do not span R3. Determinant of A coefficient A here is 0 means that you can't find the inverse of the system of linear equation here, and you can't find the solutions for it. And that's why we prove that there's no solution for this system of linear equations, and thus v1, v2, v3 do not span R3. But if you find out that the determinant of A does not equal to 0, so the system of linear equation has a consistent solution, and thus v1, v2, and v3 do span the R3. And do not get confused with the previous lesson. In the previous lesson, we want to check whether an object, a given object, is a linear combination of those fundamental components. So to check whether it belongs to the vector space or not, is it a member of the family? In this lesson, we want to check whether the given fundamental components can span the space or not. Or you can use it to generate any objects in their space, or can form the members for the family.